All right, well, good evening and welcome to lecture 4 of MT225. Uh, Tonight, our main focus is going to be on looking at vectors. And we're going to start out with a little less than mathematical treatment of vectors. We're going to look at the basic principles and learn a couple techniques that'll help us out later on in making sure that we've done our calculations correctly. So it's good fundamental information. Wednesday night's topic will be how to do some of the things we're going to be learning about tonight, how to do these mathematically. So we're going to look at more of a graphical approach to vectors this evening. So first off, any adding and dropping, make sure you get that taken care of here. It's going to start getting difficult really quickly to add into the class if you haven't already. Got plenty of time to drop, though hopefully no one will find themselves in a position where they feel they need to drop. As I mentioned in the first class, if you get into a situation like that where you're starting to think maybe I should be dropping the class, talk to me first, and we can take an objective look at your situation and see whether it's reasonable to continue. In most cases, it is. Um, Homework 1 is up on the website, and that is due on Wednesday night. And for the moment, I haven't heard any news yet about whether or not we have a room. We're continuing to press on both the administration side and on the county side here to try to see if we can get someplace to be in. But for the moment, we're sticking online. So likely Wednesday night will be online as well. Perhaps next Monday night we'll be able to be in a classroom somewhere. So homework is due on Wednesday night. It's due prior to the end of Wednesday. So 11:59 p.m. on Wednesday. Make sure you've emailed it to me or texted it to me, got it to me somehow, so that I can take a look at it and get it graded. The website, YouTube channel, all that information, that's just our standard content. So now that we have a homework assignment out there, are there any questions on the homework? All right. Well, I'll ask the same question again on Wednesday. Hopefully, the silence is more of a sign that this is fairly easy so far and have no one's really run into difficulties yet, and not so much that people haven't bothered to look at it yet, though. Chances are there's some of you out there who haven't had a chance to look at the assignment yet. I was usually amongst that group when I was in college, so usually the night before, so it always seemed like a good time to start the assignment. But Wednesday night, I'll open up the floor for questions on that, and we can work as a class, see if any of the problems need to be worked out in detail. But on these introductory assignments, things are usually pretty straightforward. So let's move on to our content for this evening. We're going to take a good look at scalars and vectors, and we'll actually see why a scalar is called a scalar here tonight. But scalars and vectors, what they are, what meaning they have for us, and how we can start working with them. Most everything we do in this class, at least in the first 2/3 of it, involve vectors in some way because we use forces, and forces are vector quantities. And we'll learn what that means here tonight. And we'll do a little bit of graphical vector math. We'll learn how by sketching things to scale and in the right directions, we can combine vectors together and do essentially mathematical operations. Now, granted, the precision is not very high. When you're just drawing things out on paper, the lengths that you draw and the angles you draw have some pretty big errors to them. The size of your pencil point or your pen point can be a pretty significant size. So we don't get a lot of precision out of doing graphical vector math, but it lets us know if we're in the ballpark or not. It gives us a pretty good idea of how things are going to lay out. So it's a good backup to our mathematical calculations, where all too often we can get tied up in the numbers and forget what the picture actually looks like. So we want to keep a good idea and a good focus on that picture. So let's take a look at scalars and vectors. Well, even though the name might be a little bit strange to you, the word scalar may not be something you've heard very frequently, if at all. You're very familiar with the basic concept. Scalars are the regular numbers that we are used to using. Scalar math is pretty familiar to you. You've been doing scalar math most of your life. So a scalar, technically speaking, a scalar is a quantity, or it references a quantity that can be completely described by a single number. So one number does the whole job, tells you everything you need to know. For example, temperature. Temperature is a great example of a scalar because one number tells you the whole story. You might need units on that number. For example, if I say it's 28 degrees Fahrenheit out, just with that number, you know what the situation is. I don't have to add any extra information. So scalars are completely and totally described by one value. Not all quantities out there are like that. Vectors need more information. One number doesn't do the whole job. One number doesn't communicate everything when you're dealing with a scale, when you're dealing with a vector. So math with scalars, pretty easy and familiar. All of the adding and subtracting and multiplying and dividing, chances are that you've done have all been done with scalars. If you've had some more mathematical or physical background, maybe you've done some work with vectors already, but that's not a prerequisite for this class. So math with scalars, pretty comfortable. And in fact, we're going to rely on our mathematical skills with scalars. We're going to break down on Wednesday when we work on analytical vector math, doing math with vectors and numbers. We're going to find that we can break it down into basically doing scalar math. We just do it twice. We do two problems instead of one. But we're going to see that theme repeated, just like we saw in the A&P program, how we're going to build a skill and then build something on top of that, and build something on top of that. So it's always a continuous process of building on what we've already mastered. So we're going to assume that you know scalar math. You can add and subtract numbers. You can multiply and divide numbers. We'll learn how we can apply that on Wednesday to working with vectors. So some common examples of scalars. Time is a pretty good scalar. Whether you're talking about the time of day or whether you're talking about how long it takes for something to happen. For example, the length of our class. That's just a number. Once you know that number and you have the right units on it, you have the whole story. There's no other information missing. Temperature, like I mentioned, is a pretty good example. Volume, that is, I suppose either volume would work. Volume in the sense of how much space there is inside something, like a gallon of milk, 231 cubic inches of volume. Or volume in terms of loudness, how many decibels we're talking about, things like that. Both of those would be perfectly fine scalars. Mass is a pretty important scalar. That's why that one's bolded in there. Mass is pretty important to what we do in this class. Mass is just essentially a count of how many molecules make up something. So it's a scalar quantity because it's just a count. Distance, how far it is from one place to another. Or how long a part is, or how close two things are fitting together. Those distances are all examples of scalars. And speed, how fast we're going. How fast we're going is not something we're going to deal with much in this class, but it is a pretty important example of a scalar. You have on your car a speedometer. It tells you how fast you're moving over the ground or how fast your wheels are turning at the very least. Those are all scalars. So how is a vector different? Well, vectors have to have some extra information. We can't get away with just one number to describe the vector. It won't tell us the whole story. Good example of this, one good example of this is the one we'll be dealing with most often, what we call force. We know that force from our previous look at physics, forces control motion, forces influence motion. But just saying how hard I push or pull on something isn't enough. I can say that I push on something with 1,000 pounds of force. How it moves depends not just on how hard I push, but what direction I push in. Pushing 1,000 pounds to the right versus pushing 1,000 pounds to the left versus pushing 1,000 pounds down. Those are all going to result in different motions. So just saying we're dealing with a force of 1,000 pounds really just isn't enough. We also have to have that direction. We have to have some additional information. So vectors require that. Vectors require more than just a number, usually some information about direction. So vectors are quantities that require at least two pieces of information. I like to think of it from a point of view of information. How many boxes do I need to fill in to completely describe this thing? You can kind of think about it like what we did with tools and hardware and all of that. To describe a bolt, you needed to have a whole bunch of different information. You needed to know what its material was, what its diameter was, what its length was. All of those features had to be fully described, or you didn't have a good picture of what the hardware really was. Vectors are the same way. We need a certain number of pieces of information. And for our class, that number is going to be two. If you go on to more advanced work, you'll deal with three-dimensional vectors, maybe even four-dimensional, five-dimensional, where you need more and more information to fully describe that vector. But our class is a completely two-dimensional class. Everything that we work with takes place in the surface of the page or the surface of a board. So vectors in our class will only need two pieces of information. So we can set up that description of a vector by either telling what the magnitude and direction are, so how much we're dealing with and what direction that quantity is applied in. Force is a good example of using magnitude and direction. How hard are we pushing and what direction are we pushing in? Think about with an airplane, for example, a jet engine produces thrust. Well, if we're producing thrust down the runway, hopefully we're accelerating the airplane. If we're using our reversers and producing that thrust in the opposite direction, we're going to slow the airplane down. The direction matters. Think about thrust vectoring, for example. That involves taking the thrust, the force from the engine, and pointing it in different directions to obtain a new flight control. So magnitude and direction, size and direction are important quantities. We can also work with that in terms of with vectors in terms of just a set of numbers. Directions can sometimes be a little tricky to deal with. Directions can be just described in words by saying up and to the left. It could be described by sort of a compass heading saying, well, north, northeast, or described by an angle, 30 degrees above horizontal. There are lots of different ways to describe directions, and they're all kind of a pain to work with. When it comes down to really doing math with vectors, working in terms of a set of numbers is going to be better for us. And we'll learn more about how to figure out that set of numbers on Wednesday. But one example I could give of this is think about navigation. If I'm going to fly from point A to point B, I might describe that flight as point my nose at heading 030, 30 degrees, and fly for 100 miles. That would be a magnitude and a direction. How far do I go and what direction do I point in? I could also do that in terms of a set of numbers. I could say, well, go so many miles east and then go so many miles north. I can break that up into two numbers that get me eventually to the same place. So you can think of it in sort of a navigational sense. A vector can be described by a size and direction. How far do you walk or fly in what direction? Or how could you get there just by following latitude and longitude. How could you go so many miles east, so many miles north to get to the point you're interested in? Both methods of describing a vector have value. Magnitude and direction give us the best picture most easily, lets us draw it out on the page most quickly so we can get an idea of what it looks like. But as far as calculations go, working with a set of numbers is going to be better. And one of the big skills we're going to learn is how we can flip back and forth between those two descriptions, whether we're dealing with magnitude and direction or whether we're dealing with a set of numbers. So we'll see that on Wednesday. So for our purposes, vectors are two-dimensional, so only two numbers will be needed to describe our vectors in class. And because there are directions involved, and because the descriptions of vectors can be different, math with vectors is a little more challenging than math with scalars. Fortunately, I'm going to show you how we can decompose essentially vector math into scalar math and do two scalar problems instead of one big vector problem, and that'll make it a little easier to work with. So some examples of vector quantities. The biggest one that we'll deal with is going to be force. So force is at the top of my list as far as what our vector quantities are. Other examples would be things like flow or flow rates. When you think about something flowing through a pipe or down a river, uh, it matters how much is flowing, how many gallons per minute are going by. It also certainly matters what direction it's going in. Um, if you've got a sewer pipe going from your house to your sewer, you certainly hope it's going in the direction away from the house. When it switches direction, bad things happen. So flow and flow rates have direction information in them. Sometimes that direction is obvious. It can only go one way, but in other situations it may not be. Think about airflow around a wing and what happens during something like a stall, how the airflow directions can change. So we have a quantity and we have a direction involved. Weight is a vector. In fact, weight is an example of a force. Fortunately, the direction of weight is always pretty easy to figure out, since all of our problems take place at the surface of the Earth or nearby the surface of the Earth. The direction for our weight vectors will always be straight down. Um, Displacement is a sort of fancy way of saying a vector associated with distance. Distance is just how far it is from point A to point B. Displacement is telling you what direction do I go in to get from point A to point B, and how far do I go? So the size part of displacement we'd call distance. So what we could say is the magnitude of displacement. Magnitude is a word we'll be using quite a bit on Wednesday. Magnitude is the size of a vector. It's how physically big the vector is or how much it represents. And the size or the magnitude of displacement is just a distance. Displacement adds an extra direction bit of information to it. Same kind of relationship is there between velocity and speed. Now, in most situations in everyday language, we treat velocity and speed the same way. Velocity and speed, they're interchangeable. But there is a physical difference between them. In physics and engineering, velocity is a vector while speed is a scalar. So if you think about your speedometer in your car, all that's telling you is a number. It's going to read the same whether you're going north, south, east, or west. It doesn't care what direction you're going in. So your speedometer is just telling you the scalar value, speed. Velocity would have to have some direction information to it. So, for example, take driving on the thruway. Around here, the thruway runs east west. So, if you're around here and you're driving at, let's say 75 miles per hour east, eventually you'll end up in Albany. But if you drive 75 miles per hour west, you'll eventually end up in Syracuse. Direction definitely matters. So if somebody calls you up and say, "Well, I'm driving at 75 miles per hour on the thruway," without that direction information, you don't know where they're going to end up. The direction information matters. So velocity has direction built into it. Now, if you happen to have in your car a compass, you could turn your speedometer essentially into a velocimeter where it could tell you both the speed, how fast you're going, and with the compass telling you what direction you're going in. So you've got both of those pieces to determine your velocity. So those are some examples of vectors. The vast majority of problems we'll deal with involve forces. So how do we know we're dealing with a vector? How do we write the vector down? Vectors we usually represent graphically by using arrows. An arrow automatically has some information about direction in it, since there is a head and a tail on the arrow. Motion or direction is generally implied to go from the tail of the arrow to the head of the arrow, from the blunt end to the pointy end. So the direction is built in. We need something to represent size. And the most natural thing to represent the quantity, the magnitude, or the size of the vector is length. The longer we draw the vector, the more it represents. The shorter it is, the less it represents. So we have both pieces of information there by drawing an arrow. The length represents the magnitude, how much we're dealing with. The direction tells us the direction of the vector. So here on this slide, we've got a whole bunch of different vectors. I've got some arrows drawn out, and we've labeled them with letters A, B, C, and D. A vector doesn't have any inherent tie to a coordinate system. So we can't really assign direction, say, for example, in angles just yet. And we're going to talk about coordinate systems on Wednesday night. But just drawing an arrow on a page, knowing that A is kind of to the upper left or upper right, B is to the lower right, C is to the upper left in direction, D is a pretty large vector, mostly to the right, maybe a little bit up. That's enough of a description for now of what those vectors are. So that's how we'd represent vectors on a page. And if we were being really careful about it, we'd have to draw these things to scale. By using a scale and saying maybe 1 inch equals 10 pounds, we could draw out a reasonable approximation of how much force we're dealing with. If we needed a direction that was very specific, we could break out a protractor and get our angles correctly established. That's usually going a little bit beyond what we need for this class. Usually a rough sketch, roughly to scale, will give us a pretty good idea of how things lay out. And that's about as far as we really need to go with it. When we do need the lengths to be relatively accurate, I'll show you a technique to help you out with that, like what you'll be getting on your new homework assignment coming out on Wednesday on homework 2. You're going to have to do some of the kinds of problems we're going to practice on tonight. And the easiest way to get those vectors drawn to scale is to just trace them. Print out the page, put another page on top of it, and trace them out, rather than trying to measure them and draw out angles with protractors. But those are just some examples of vectors, and we'll practice with a few of those here in a little bit. Now, one of the things we'll be heading toward as we get a little bit further in is looking at doing calculations with vectors. And when we do calculations with vectors, we need symbols to represent the vector. And we need to distinguish between a quantity that is a vector quantity versus one that's scalar. And typically, the way we do it in our symbols is to make the symbols for vectors look different than the ones we use for the scalars. Usually, a letter just written out normally with no special features, we assume that's a scalar. So all the equations that I've written down so far, all the x's and y's, things like that, those are all scalar quantities. A signal that we're dealing with a vector is when the letter has an arrow over it. So, for example, it might look, let's see here, might look something like, let's see, there it is. Might look something like that. So if I've got the letter F here, just written as the letter F, that's a scalar. If we put an arrow over it, now it's a vector. That kind of symbology is used pretty frequently. So for example, acceleration. Acceleration is a vector. So we'd put an arrow over it. Sometimes people write the arrow just with like one little point on it like that. As long as the direction is implied, we can have some idea that that's a vector versus the scalar quantity. Then might also see it as having a bar over it. So getting rid of the little barb on the arrow, just putting a bar over it will signify that it's a vector, or it's written in bold. So for example here, X with a bar over it represents a vector. Or a little hard to do with a pen, but if it's written in boldface, that's a vector versus a scalar. So we'll see some of those, especially if you're following along with a textbook. You'll see some of those symbols used. And if you're not clear on what those mean, you can always go to the front of your whatever textbook you're using, and it should tell you what those mean, what those symbols mean. So let's get into a little bit of vector math. First off, any questions on vectors so far? Nothing too scary, hopefully, so far. So let's do some math. There are basically 3 different operations we can do with vectors. The simplest one is multiplying a vector by a scalar. So that'll be the first one we'll take a look at. We're going to look at vector operations graphically using this arrow representation. By combining vectors and doing operations on vectors graphically, we'll get a better feel for how vectors combine, and we'll get a check on our calculations that we'll be doing a little bit later on. And so it's a useful technique to kind of keep in your back pocket to visualize how something's going to work out. We would never do any design work or real analysis by using these kinds of methods. These are just strictly sketch it out, get a rough idea of how things look. You wouldn't want to be flying in an airplane or in a building that was designed using only graphical vector math. It's just not precise enough. Round off error will make your results inaccurate really quickly. But it gives us a good basic picture of what things look like. So our operations are going to be scalar multiplication, vector addition, and vector subtraction. Those are the 3 basic operations. The ones we'll lean on the most, the one we'll lean on really the most that we'll use and has the most practical use to it is vector addition. That's what we're going to learn how to do on Wednesday night mathematically. So being able to do it graphically gives us a backup, gives us a way of looking at our answer ahead of time and seeing what we should expect. It'll also help us to draw things in the right directions later on when we draw up sketches and we do other work. So, but these are the operations that we're supposed to cover in order for to meet the objectives of the class. the most useful part of that is going to be vector addition. So let's take a look first at the simplest of the operations, which would be scalar multiplication. Now, if you look at that word scalar for a second, you might pretty easily pick out the kind of root word scale. When you scale something, it's essentially zooming in or zooming out. When you change the scale on a map, go from 1 inch equals 10 miles to 1 inch equals 1 mile, the size of the map changes. Scalars, we've learned, reference numbers, just tell us about numbers. When we apply a scalar to a vector, when we multiply a scalar and a vector together, that scalar changes the size of the vector. It scales the vector. That's why they're called scalars. They can be used to scale the vector up or down. If I want to make the vector bigger, I multiply by a number bigger than 1. That will scale it up. So if I want the vector to be 10 times bigger, I multiply the vector by 10. If I want to make the vector smaller, I multiply by a number less than 1. That will scale the vector down. So if I multiply a vector by 0.5, it's going to cut the size of that vector in half. There's one little quirk, though, with scalar multiplication, and that's dealing with negative numbers. Negative scalars can be used, but negative scalars flip the direction of the vector in addition to changing the size. Think about it as having something that's pointing to the right. If you multiply it by something negative, it becomes a negative number. It's going to go to the left. Negative scalars flip the signs, or flip the directions of the vector. So we'll see some examples of each of these here. So if we multiply by a positive scalar, what that does is it changes the size. It changes the magnitude of the vector. Positive scalars don't change direction, they only change the magnitude. Negative scalars will change the magnitude, but also flip the vector around. It'll reverse the direction. And if we just multiply by -1, just like multiplying a regular number by -1, if I multiply 5 times -1, I get -5. I get the same number, just flipped in the other direction. Multiplying by -1 just flips the direction. So let's see some examples of those here. So let's start out with a vector. So I'll draw a vector here. I'm gonna make that vector, let's say 2 inches long. So there's my vector. Maybe we'll call that vector A. Now, if I want to multiply vector A by 3, so I want some new vector. Let's call that vector B. I'll draw some arrows here. So vector B is going to be 3 times vector A. Well, the scalar 3 will just make this vector A 3 times longer. So I'm going to end up with a vector that is in the same direction, but 3 times longer. So let's try and draw that out. In order to be in the same direction, I've got to get the same angle. I don't have to draw it right on top of it. You can draw it anywhere you want. That's one of the useful things about vectors. You can draw them anywhere you want. As long as you have the right size and the right direction, it's fine. So I'm going to start down here and get, let's see, 1, 2, 3, 4, 5, and 6. So there's vector B. Vector B, same direction as vector A, but 3 times larger. That's scalar multiplication. So that's multiplying by the scalar 3. It made the vector 3 times bigger. Let's try vector C. And we'll make vector C 0.5 times vector A. So we'll multiply vector A by 1/2. That's going to keep the same direction, but it's going to reduce the size of vector A. So I'm going to end up with a vector in the same direction. So I'll line the direction up here, but it's going to be half the length. My original vector was 2 inches long. So now my new one, vector C, is half the length of vector A, so it's 1 inch long. So those are scalars. Scalars change the size of the vector. So scalars bigger than 1 make the vector bigger. Scalars less than 1 make the vector smaller. A scalar equal to 1 would just keep the vector the same size. Just like we know from arithmetic, when you multiply by 1, nothing really changes. Let's see what happens if we multiply by -1. Let's take vector D and make that -1 times vector A. Well, multiplying by -1 won't change the length of the vector. So I'm still going to have a vector that's 2 inches long, but it's going to be pointed in the opposite direction. So over here, I'm going to line it up so I'm in the same direction, same length of 2 inches. But now vector D is opposite the direction of vector A. The negative sign just flips the vector around. So let's see, one more here. Let's do vector E. I think we'll hit every possible combination here. Let's do -2 times vector A. So if you're not watching this live, or if you're watching this on the recording, pause it for a second and try to come up with what the answer is going to be, and then check with the video when you're happy with your answer. Here we've got a negative scalar, so it's going to flip the direction. So it's going to be pointing in the same direction as D, opposite A, but the 2 is going to make the vector twice as long. So I'm going to have my original vector was 2 inches long, pointed to the upper right. Vector E is going to be twice as long, so it'll be 4 inches long, but it'll be pointed to the lower left. So the way we draw that in there, we get that angle right. And there's vector E. So vector E is twice as long, but has been flipped in the opposite direction. Those are really all the options as far as vector and scalar multiplication go. You either have something just blow the size up or cut it down, or flip the directions. I suppose one example I didn't do that would not be in this list, but that would be a possibility, is a negative scalar less than 1. But if this is making sense, you should be able to figure out what that does. It's just going to flip the direction and make the vector smaller. Anything not quite making sense on vector multiplication with scalars? All right, so let's try some vector addition then. Vector addition, far more important than scalar multiplication. So really make sure you've got this down, and if you have to go back and watch it again and make sure it makes sense, go ahead and do so. So the first thing we have to understand in order to set up vector addition is something I mentioned just a few minutes ago, is that it doesn't matter where you draw a vector. That may be somewhat strange to you. If you've dealt with vectors before, you might have had somewhat overzealous math instructors in the past saying, well, you always got to draw your vectors at the origin, always draw them outward from the origin. Well, that works in a math class because they're going for certain things. But in reality, vectors don't need an origin. There's no requirement that there even be any kind of coordinate system there. Vectors transcend that, they exist without it. So a vector can be drawn anywhere you want as long as it has the right size and the right direction. It doesn't matter where it's drawn. The fancy way that we state that in dealing with vector math is we call it the parallel transport theorem, and it's really just a fancy way of saying that as long as you draw a vector so it has the same length and direction, it doesn't matter where you draw it. So essentially, what the two parts of that, when they say parallel transport, parallel means same direction. Transport means to pick it up and move it around. So two vectors are equal as long as they have the same magnitude in the same direction. And it doesn't matter how I move them. I can move them around anywhere I want in the page as long as they maintain the same direction and the same size. So a vector doesn't care about what origin or what coordinate system we're dealing with, and we don't even need to use a coordinate system for anything we're doing tonight. So we can move a vector anywhere we want as long as it stays parallel to its original depiction. And sometimes that is drawn from an origin, though we don't really have to do that. So let's switch back over to the camera here and I'll illustrate the idea. So let's start with, let's go back to a vector here. Let's take that vector. We'll make that vector A. The easiest way to think about vector equality is to imagine being able to pick this up. Imagine being able to pick that vector up and move it anywhere you want on the page. Now, if you pick that vector up and you stretch it out or you shrink it, you've changed the vector. It's no longer representing the same amount. If you twist it, making it point in a different direction, it's no longer the same vector. But if you keep it parallel to itself, keep it parallel to the direction it was pointed in. So you pick it up and move it around, but you keep it pointed in the same direction. And you don't stretch it out or shrink it. The vector is going to stay the same. It still represents the same amount. So no matter where I draw a 1 inch long vector pointed in that direction to the upper right, these are all the same vector. So these are all properly labeled A. These are all the same vector. They have the same length and the same direction. That's what parallel transport means. You can imagine picking this up and just keeping it parallel to whatever direction it originally had. As long as you don't turn it, as long as you don't stretch it or shrink it, it's the same vector. That'll become useful here in setting up vector addition, because the easiest way to do vector addition is to set it up so our vectors are in a certain pattern. And that pattern involves the head and the tail of the vectors we're combining. We want to position those close to each other. So let me show you how vector addition works by showing you how essentially scalar addition works. If you think way back to maybe grade school, you probably dealt with number lines. Now, a number line, we have marks on them, kind of like that, and maybe -1, -2, and so on. We have a number line. Well, if you had to add 1 and 3, one of the ways you might have learned how to do it was to say, well, I'm starting out here at 0 and going to 1. And then from 1, I'm going to go 3 more. So you did the addition essentially has two steps. To add 1 and 3, you went from your starting point to 1 and then went from 1 3 more spaces. Essentially, you had two arrows here, one representing 1 and one representing 3. The answer was 4, 1 plus 3. We could write that as one arrow going from the origin to 4. Could even label it 4. That's the idea behind scalar addition, essentially. In fact, you can kind of make it work out with both addition and subtraction. We'll come back to this here when we take a look at subtraction. Notice how the arrows are set up here. There's a sequence involved. You start at some point and you go to some point, and then when you deal with your second piece of information, so dealing with the 1 took you from the origin to the point on the number line labeled 1. Then dealing with your second piece of information, you didn't go back to the origin. You started where you left off and then took into account that 3. We've arranged these arrows so that the tail of the second arrow, the one that's associated with the 3, is at the head of the first arrow. So when we're dealing with arrows, so I'm going to draw another arrow down here. That pointy part of the arrow, we call that the head of the arrow. And the not so pointy part, where the feathers would be, that's the tail. When we add vectors together, we arrange the two vectors so that the head of one vector is at the tail of the next one. Or put a different way, the tail of the second vector starts at the head of the first vector. Now, this was all along one line. Vectors can point in any direction. So we might need to move some things around to arrange them properly. When we added these two scalars together, we had our 1 and our 3. The answer was an arrow drawn from where we started to where we finished. That took into account both pieces of information, both the 1 and the 3. And the answer is going to be the same thing when adding vectors. We add two vectors together by first arranging it so that one vector's tail is at the head of the other. And then we draw a line from the tail of the first vector to the head of the second. That's our answer. So let's see how that works here. Let's go back to the screen. There we go. So the basic idea behind vector addition. So we'll have two vectors, A and B, that we're going to add together, and that's going to give us our result, vector C. We use the idea of parallel transport, that we can move vectors around wherever we want, as long as we keep them parallel to their original picture. So we don't turn them, we don't stretch them or shrink them. We place the tail of one vector at the head of the other, and then we draw a line between the tail of the first vector and the head of the second. That represents the sum, just like the arrow going from the origin to 4 was the sum of 1 and 3. So let's see how that works here. Let's take two vectors here. Let's take vector A, which I'll make as a just as our first kind of simple example. We'll have vector A here, and we'll have vector B. So vector A is pulling to the right, and it's 1 inch long. And then I'm going to have vector B 2 inches long. So those are my two vectors, and that's how they've been drawn out in what's been given to me. I want to add these. I want vector C, which is vector A plus vector B. Now, remember that addition doesn't care about order. Addition is what we call commutative. Doesn't matter what direction we or what order we do things in. So we can work with A first, we can work with B first. It doesn't make any difference. So I'm going to redraw this just a little bit. I can redraw A anywhere I want. So I'm going to redraw A down here. As long as I keep it the same length and in the same direction, those two vectors are still the same. Vector A and vector A are the same. And here's where the trick is. I'm going to deal with vector B a little bit differently. I'm going to arrange it so that the tail of vector B is at the head of vector A. So imagine I can pick up this vector and drag it around and drop it so that its tail starts at the end of A. That's what I'm going to be doing here by drawing it. So I'm going to draw vector B. I'm going to make sure that goes straight up, same as vector B did in the original drawing. And it's the same length, 2 inches. There's vector B. You got to get that arrangement right first. It's always got to be head to tail. So the head of A and the tail of B are joined together. So imagine this kind of like navigation, I suppose. You go a certain number of miles east, then you go a certain number of miles north. You're doing these in sequence. A plus B means do A first, then do B. So the tail of B has to be at the head of A. The answer, the sum, this is just the setup. This is like saying 1 plus 3. You haven't given an answer yet. And sometimes I see people stop right here. They get this set up and they say, okay, I'm done. No, you're not quite done. You have to actually add the vectors together. And the way we add the vectors together, just like we have learned to say 4 when we've got 1 plus 3, here we draw a line. We draw a line starting at the beginning of A. We start at the tail of A and we go to the head of B. So our answer graphically, vector C, is an arrow starting at A, at the head of A, and going to the tail of B. That is A plus B. That's vector C. So the sum of A and B is C. Now, what does that represent physically? Think about these as if they were forces. If they were forces, vector A is a pull to the right and vector B is a pull up. You'd expect if you had some sort of object hooked up to these two forces, vector A pulls to the right, force A pulls to the right, and force B pulls up, you'd expect the object to travel up and to the right. That's what vector C is showing. Vector C is showing the combined effect of these two vectors. So there's to the right and there's up. Vector C has both of those. You'd also expect, if you were going to put these two forces on there, that they're going to combine. They're going to increase the amount of force that you've got. Notice how vector C is longer than either A or B. We've got a bigger value because A and B partially work together. They're not working as much together as they would be if they were both in the same direction, but they are increasing the amount of force that's on the object. Now I want to show here also that order doesn't matter. So let's go off to the left side here and I'll deal with vector B first. So let me draw vector B first and show that vector C also will equal B plus A. It doesn't matter what order you go in. So let's draw vector B. If we were doing B plus A, we'd draw B first, Then we draw A with the tail of A at the head of B. So here's vector A. B plus A, starting at B's tail, B plus A. So my answer is going to join the tail of B and the head of A. And if I draw that out, we get the same exact vector that we had over here. Same length, same direction. To within, my ability to draw it with this. So I've got about, 2.2. These are in tenths, right? Well, yeah, scale is about the same length. Direction looks about the same. And two vectors are equal if they have the same length and the same direction. So that's the basic idea with vector addition. And we can do this with any two vectors. In fact, we can do it with any number of vectors. Just like we can take numbers and say 1 plus 3 plus 5. We can do them all in sequence and do our sum just by drawing an arrow between where we start and where we finish. So let's try another example here. Let's say we have something a little more sophisticated. We'll do, let's say, vector A here, and maybe vector B there. Not quite the nice angles I had in the first example. Well, I want to see what happens when we have vector A and vector B added together. I want vector C to be vector A plus vector B. We work it exactly the same way. If you want to start with A, draw A first. So we can draw out A. Let's say, let's get the angle right there. There we are. So there's vector A. Then you got to pick up vector B and set it up so the tail of B is at the head of A. So we'll get the angle. So there's vector B. Our answer, C, is going to be an arrow joining the tail of A to the head of B. So it's A, then B. It's essentially a shortcut. It's the straight line between where you started and where you ended up, rather than going through this intermediate point. So we can draw a line right there. That would be vector C. Now watch what would happen here if we did vector B, then vector A. We're going to get the same answer, but if I draw it all on top of each other, if I pick up B and bring it over here, so I'm going to have something like that. If I pick up B and put it there, and then pick up A and draw it there, so here's B, here's A. B plus A gives us C. A plus B gives us C, because they both take us to the same point. It doesn't matter what order you do things in. The diagonal of this parallelogram is our sum. So when we're dealing with vectors, it doesn't matter what order you go in, when you add, you'll always end up in the same place. Any questions on those two? Let's try one more example here. I want to show what happens when we've got, let's say, 3 vectors to deal with, and then we'll take a look at vector subtraction. So let's take something that looks sort of like this. Let's say we'll make vector A there. vector B there, and maybe let's say vector C. So I've got these three vectors, vector A, B, and C, and I want to know what the sum of all three of these vectors would be. So I want, maybe we'll call it vector D. I don't have to give it a name. I'm just doing that for convenience. So I can write it down in an equation. D is going to be A plus B plus C. So we draw it out. We do exactly the same thing we did in the previous two problems. We set it up so that the vectors are arranged head to tail. So we'll draw A, then we'll draw B with the tail of B starting at the head of A. Then we'll draw C with the tail of C at the head of B. Our answer will be a line between where we started with A and where we ended up with C. So let's try it out here. Let's draw it over here. We've got vector A. Then we've got vector B. And then we need vector C. And so vector C draw something like that. So vector A, B, and C. We're going A first, then B, then C. And our answer is going to be a line from the beginning of A to the end of C. And we get something that looks sort of strange, but sort of like that. That would be vector D. Now, if you don't like how it lays out in a particular arrangement, like maybe this was a little bit awkward the way that it's drawn out, change the order. Go vector B first, then A, then C. Or go C, then B, then A. You'll get the same answer each time. So let's try it a little bit of a different way here. Let's take, we'll take B first. If we do B first, then A, then C, maybe that'll arrange, that arrangement will be a little nicer to look at. The answer is going to be the same, arrow from where we started to where we finished. So something like that. That would be vector D. So that's the basic idea behind vector addition. Make sure you really see that, because that's going to be useful to us in a lot of different places. Like I said, we don't do it. We don't use it for design. We don't use it to do our math. We're not going to measure out the length of D and figure out, well, how many pounds of force that represents, or break out protractors and figure out what the angles are. But it gives us a good way to figure out, well, what direction is my answer going to be in? Here I can see just by sketching this out that I should expect, even though I've got all these forces acting in different directions, most of the result is going to be to the right. I'm going to end up with something that's substantially horizontal. And that's a good piece of information that can be used to help understand the problem. So that's the basics behind vector addition. Any questions there? All right, let's take a look at vector subtraction then. Well, most of you, in fact, all of you, well, almost all of you have had math with me. And you may recall that when we started talking about subtraction, what I encouraged you to do was not do subtraction. To avoid subtraction, because subtraction causes all sorts of problems. Instead, add the opposite. So rather than subtracting, doing 5 minus 3, we would add 5 and the opposite of 3, -3. That way we avoided all sorts of problems. We used the keep change rule and things like that to figure that out. In vectors, we can do exactly the same thing. Vectors work the same way. And to see that, let's go back to our number line. So if we go back to the number line here, and let's say I wanted to get 3 minus 2 off of the number line. So think back to what you might have done maybe in grade school or something when you learned about how to do math with number lines. What you would probably have done was you'd start at 0 and you'd go 3 to the right because that was what the 3 represented. So we'll draw that as an arrow here, 3 to the right. But then you wouldn't go another 2 to the right. You'd use the fact that this was subtraction, this negative. What you'd really be doing is saying this is 3 plus a -2. That's what keep change does. It keeps this first changes the subtraction to addition, then flips the sign on the second number. Knowing what we know about scalars and vectors, that negative just flips the direction. If this was just a plain old addition problem, 3 plus 2, you just draw another 2 to the right. But because there's a negative, it flips it around. So essentially what we've got is an arrow of length 2, but going to the left. And that puts you right at 1. Your answer would be right there. So you've got 3, 2, and 1. Well, think about that in a vector addition kind of sense. Adding 3 was starting at the origin, going to 3, and then going back 2. Our answer was a line from where we started to where we ended up. That's where 1 is. So vector subtraction is really just vector addition with a flip of one of the vectors. The second vector gets flipped around before we add it. So let's see how that works. So let's say we've got a minus b. Multiplying by -1 just flips the direction of b. So what we do is when we go and redraw it, we flip the direction of b. That'd be -b. And then we just do vector addition. We treat it as a different vector. So let's see how that works. Let's take the same two vectors we started with on our first example. We'll have a there, and we'll have b up like that. Now this time I want c to be a minus b. We're going to start out the same way by drawing a. But remember here with subtraction, just like with arithmetic, subtraction order matters. So you can't do it whatever way you feel like. You have to start with a and then subtract off b. So I'm going to start off by drawing a. So I'll draw the vector over here. Same direction and length. But then rather than drawing in b, I'm going to rewrite this. I'm going to draw it as a plus -b. -b is b flipped over. So I'm going to draw a vector that's got a length of 2 inches, but I'm going to draw it down instead of up. So this would be -b. It's b, but in the opposite direction. And I drew that in the wrong place. So this is where I missed my whiteboard. Oh well, let's draw that again. Remember that when we're doing vector addition, which is what we're setting up for, we need to draw the tail of the second vector at the head of the first. So there's A. I need to start my negative B right there. So I screwed that up. Sorry about that, but it's okay. Mistakes happen. So there's negative B. So we've got A and negative B. A plus negative B gets us to right here. Our answer, as with all the other vector addition we've done, is an arrow going from where we start to where we finish. So our answer here will look something like that. Vector C is A plus a negative B, which is the same as A minus B. Now compare that to what we got with A plus B. When we did A plus B, that was up and to the right. This is down and to the right. So it's A, then minus B, B pointing down. Let's try another one of those. Let's see, let's do vector X. And vector Y. And we'll make vector Z vector X minus vector Y. So if you're watching this on the video, pause it and get it set up, and see if you can see if you match how the setup is to be done, and then see if you can get the right answer. We're going to treat this as not X minus Y, but X plus a negative Y. So this would be the same X, but I'm going to add to that Y flipped over. So I'll redraw X first, and we'll get the right angle on it there. Let's go down here. There we are. So there's vector X. Then I need negative Y. Well, Y is down and to the right, so negative Y is going to be flipped up and to the left. Drawing negative Y starting at the head of vector X. So it's going to look something like that. This would be negative Y. So it's Y flipped around. We're doing X plus negative Y. We're starting here at the tail of X, and we're ending at the head of Y. So our answer is an arrow connecting those two. That would be vector Z. Vector Z is X plus a negative Y. Now, in practice, we don't have a lot of application for subtracting vectors. Most of what we do, we deal with vectors that represent forces, and those vectors we add. Even when they're in opposite directions, we still add them, and the numbers take care of themselves for the most part. There's not usually a lot of call for vector subtraction in this kind of sense. So make sure you really focus on getting vector addition and the idea behind vector addition down. That will help you out quite a bit as we start working more mathematically with vectors on Wednesday. Anyone have any questions on adding, subtracting, or multiplying with vectors? All right. So next time on Wednesday night, I will introduce the idea of coordinate systems. Most of you have seen a little bit on coordinate systems. We dealt with Cartesian coordinates in the first semester. I'll introduce another coordinate system that we call polar coordinates, and we'll see how that relates to vectors, magnitude, and direction. Then we'll spend the rest of the time on what we call analytic vector math. So this was graphical vector math, being able to draw things out. Analytic vector math involves doing analysis, working with numbers, and doing so in a much more precise way than we could ever do drawing things out graphically. So the practice that we'll be doing will be reinforced by pretty much every problem that we do for the remainder of the semester. We're going to involve some sort of vector math in almost every one of those problems. So really important content next time. And so we'll be spending a good bit of our practicum session doing practice problems. And while you may not have hung around yet for any of the practicum sessions, I would strongly encourage you to do so on Wednesday to really get a little more practice with adding vectors, because it's if you can get that down, you've got pretty much every problem that we will be doing. You've got the basic skill that you need. So it's really one of those fundamental skills you got to have working in order to make this class be a beneficial experience for you. So that'll be next time. Anyone have any questions? All right, well, we are just about on time. So we're going to go ahead and take our break. If you have homework questions or want to work out anything more on vector operations graphically, come on back in about 10 minutes and we'll work on some practicum problems. Otherwise, have a good evening, and I'll see you on Wednesday night.